Okay, class, welcome back. We're going to start from the beginning of this chapter on nuclear chemistry and then slow down a little bit when we get to the new material. But if you remember, we did something called nuclear notation. It's going to be important that you remember this. This is from way back in chapter 3, I believe, so it's been a long time since we've seen this. But essentially, you remember that the 12 and the 6 here represent two different numbers, obviously, and this is kind of important that you remember how to do this. But Z is the atomic number. The atomic number is the number of protons, which tells you two things. It essentially tells you the identity of the element. In this case, the only element with atomic number 6 is carbon. And because it tells you the number of protons, which number 1 tells you the identity of the element, it also tells you in a neutral element the number of electrons, because we know in a neutral element the number of protons, in this case, carbon's case, is 6. In a neutral element, he also has to have 6 electrons. So again, the number in the lower left-hand corner is the atomic number, and it tells us the number of protons, which identifies the atom, but it also tells us in a neutral atom the number of electrons, because those have to be equal. And of course, we have the atomic number, or the mass number for A, okay? The mass number A is representative of the number of protons and neutrons. So this is where you're going to find the mass, hence the name, the mass number. Protons and neutrons have about equal mass. When you add them together, you get the actual mass of the atom. Remember, electrons' mass is so small, you can ignore it. It's negligible. So all the mass of an atom is found, if you'll remember, in the nucleus of the atom, and it's made up of protons and neutrons, and the charges are the protons, positive charge of protons, and the negative charge of the electrons. So that's how you read nuclear symbol. It's going to be important as a review that you're able to do that, to be able to balance what's called nuclear equations. And nuclear equations, okay, is a reaction that changes the nucleus of an atom, so nuclear reaction. Okay, as you can see down here, we have beryllium. Of course, we know it's beryllium because it's atomic number 4, and the only element with 4 protons is beryllium. In this case, it's got 9, mass number of 9, therefore it must have 5 neutrons, okay? If I react that with what's called an alpha particle here, okay, which is essentially a helium nucleus, which is made up of 2 protons and 2 neutrons for a mass number of 4, if this side of the equation, okay, this side of the equation, the mass number equals 12, therefore this side of the equation, or excuse me, the mass number equals 13, therefore this side of the equation, as you can see, those mass numbers have to equal. Okay, 9 and 4 is 13, 12 and 1 is 13. Similarly, when we look at the atomic number, the lower left-hand corner numbers, we have 4 and 2 equals 6, therefore this has to equal 6 as well, and it does. So as long as both sides of a nuclear reaction, nuclear equation, the atomic number and the mass numbers add up, you are fine. And of course, I had you work on this sample problem here in class, okay? Not very difficult, so we'll go past there, but you essentially would cause one side of the equation equal the other side. Now, there are types of radioactive decay, and you're responsible really for these 4 different charges. The first one, as you can see, is the alpha particle. It's made up of, as I said, a helium nucleus, which is to say it's made up of 2 neutrons and 2 protons together. Added together, they become the 4, get the 4 mass number there. The charge on this thing is +2, and its mass is 4, which we predicted from over here. So those things all come together. If you remember back in an earlier chapter, when we talked about Rutherford's experiment, remember he shot essentially alpha particles at a very thin gold sheet. It can be likened to shooting cannonballs at a piece of tissue paper, and you would expect all the cannonballs to go through the tissue paper. If I shot cannonballs at it, just like Rutherford was expecting all the alpha particles to go through the gold foil. However, every once in a while, one of those alpha particles was deflected or downright shot back at him. So it would be akin to me shooting a cannonball through a piece of tissue paper, and as it hit the tissue paper, the cannonball would be deflected to the left or right, or at times nailed right back at you. So obviously something else was going on here, and that's when, using alpha particles, Rutherford was able to discover, or really identify this area of dense mass, which he coined the nucleus, which we know is made up of the protons and the neutrons. And that's why these alpha particles were deflected at times, because a positive, you'll remember, will repel a positive. So if you have a positive 2 coming out of densely packed nucleus full of positives, you're going to have that phenomenon. Again, or next, the beta particle, as you can see here, is really the emission of an electron. So the alpha particle is the emission of essentially 2 protons. Beta particle is the emission of an electron. A positron, okay, which is, we'll talk about, is the opposite of really beta decay. And then gamma. Gamma is a little bit easier because it actually doesn't change a nuclear reaction at all. It's just the energy that's released. However, you're probably familiar with gamma radiation in terms of Hulk, the green monster. He was exposed, according to the comic book, to gamma radiation. That's why he's so strong. In real life, people exposed to gamma radiation develop cancer. Why? Well, here's in this slide, you see it. You see the alpha particle here, okay, that really can only penetrate so far. All right, so the alpha particle will barely penetrate a piece of paper. The beta particle is a little bit more of a serious particle in terms of energy. It can go through paper and lead, or glass will cut it down. But gamma radiation will go through all 3. In fact, some of it will come out here. All right, so even through lead or concrete, you get gamma radiation. It's very, very harmful kind of radiation that's very, very disruptive to the cellular function, and in most cases will rise the cancer rate. Okay, so let's talk about some of these emission phenomenon for a second. Let's talk about alpha emission. An alpha emission, an alpha particle, which is essentially 2 protons and 2 neutrons, is emitted from the nucleus during some kinds of radioactive decay. Now listen, it's all the heavier elements on the periodic table that experience decay. Okay, so you get a certain weight, and your nucleus becomes unstable. In order to stabilize, in this case, a nucleus will lose an alpha particle, which is to say lose 2 neutrons and 2 protons. Now, what's going to happen here? We have polonium-210 here is decomposing via alpha decay into a more stable, okay, this atom, the polonium-210, is decomposing into a more stable lead-206, and at the same time it's releasing this alpha particle. So it's all about stability going down here. Okay, so that's very simply alpha decay. It's easy. None of these decays are particularly difficult. All I would say is, whatever's on one side of the equation, as you can see back here, we have a mass number of 210 here, therefore the 206, and the 4 have to add up to 210. And similarly, if we have 84 as an atomic number here, then the 82 in lead, and then the 2 of the helium nucleus have to sum up to 84, and they do, so we've correctly balanced this. Okay? All right, beta particle. Beta particle represented by what looks like the Greek letter B there, which literally stands for beta, okay, is an electron emitted from the nucleus during some kinds of radioactive decay. So what literally happens here, and this is very strange, but, quantum mechanics, the nucleus dealing with protons, electrons, and neutrons, and the things that make up protons, electrons, and neutrons, like leptons and leptons, and all these other things make up these even smaller particles. It's an exciting area of investigation, but it's way beyond the scope of what we want to talk about here. So just suffice it to say that a neutron, every once in a while, a neutron, of course, doesn't have a charge, okay, but it does have mass, represented the 1, 0 here, okay. Every once in a while, these things can be converted into both a proton and an electron, or essentially a proton, which of course proton has a mass number of 1 and has a charge of 1, and then in so doing it also releases a beta particle here, okay? And the beta particle, of course, is an electron. So for whatever reason, sometimes neutrons can be converted into both a proton and an electron. And that's essentially what happens, as you can see in a real life example down here. Okay, this is what happens with carbon. Carbon-14, okay, carbon, if you remember, a stable isotope of carbon is carbon-12, means it's got 6 electrons and, 6 protons and 6 neutrons. In this case, carbon-14 has 6 protons and 8 neutrons. So it's a heavier nuclei, and this is what we have seeing here too, okay? You have this heavier nuclei of carbon releasing a beta particle. Now remember, we got to balance the equation here, so in order to balance this out, this side has to equal this side, so 14 plus 0 equals, but 7 times -1 is going to get us our 6. So as you can see here, this is a direct picture of a proton becoming, or a neutron becoming both a proton and an electron, okay? One of the carbon's neutrons here is converted to a proton, okay? So if I add a proton to an atom that has atomic number 6, I get atomic number 7. If I change the atomic number, I change the identity. So we go from carbon to nitrogen, and at the same time release that electron. So again, you can see very clearly here that the neutron becomes both a proton and an electron. So interesting phenomena, okay? Next is really the reverse of this, an electron capture. An outer orbital electron is captured by the nucleus of its own atom. So in this case, we have an electron combining with a proton, essentially to get back to the neutron. So again, electron capture is the opposite, really, of what we just looked at. An example of electron capture is radioactive decay of silver-106 into lead-106. Okay, so again, as long as both sides of the equation are equated, 106 plus 0 is going to get us 106, 47 plus minus 1 is going to get us 46. That is electron capture, okay? And the last thing I want you to be aware of course, is gamma radiation, gamma emission. Gamma rays are high-energy electromagnetic waves emitted from a nucleus as changes from an excited state to a ground energy state. One of the easiest ways for nuclei to become more stable is by releasing energy. The energy they release is called gamma emission or gamma radiation. As I said, it's extremely harmful. Okay, here's a picture of the UV spectrum and gamma radiation. As you can see here, this small little band right here, really right here, of wavelengths represents visible light. To the right of that, for all we know, these are pretty safe. The larger the wavelength gets, the safer it's presumed. The safer the wave is, the smaller it is. Obviously on this side, talked about going to the dentist last time and how they put you in that iron coat, or that lead coat, excuse me, to block x-rays, so it makes you feel good. But even worse than that is the gamma rays. Very, very small wavelength. Remember, wavelength and frequency are inversely related. So if I have a small wavelength, I have a huge frequency, and the higher the frequency wave, the more potentially damaging it can be, especially to the human body. That's gamma radiation. That guy's easy because, it's just energy. Okay, this is where we left off in class. We left off talking about half-lives. Well, we actually didn't get to this point. What is a half-life? Half-life is the time required for half the atoms of radioactive nuclei to decay. So you start off with a certain mass of atoms, let's say carbon-14, radioactive isotope of carbon. You start off with a certain amount of mass. The half-life is how long it takes half that given amount of mass to decompose. So if I take carbon-14, for instance, and I take 10 grams of carbon-14, the half-life is how long it takes to go from 10 grams to 5 grams. Let's say, for all intents and purposes, it's 5 years. Okay, so it takes 5 years for half the mass of a given sample of carbon-14 to decompose. So go from 10 grams to 5 grams. It takes another 5 years for it to go from 5 grams to 2.5 grams. It takes another 5 years to go from 2.5 to 1.75 grams, and so on and so forth. That is a half-life in a nutshell. Okay, some of the more famous half-lives are represented in this picture here, table 2. I don't have so much of a problem with some of these guys. This one and these two are an issue. All right, this is not a perfect science. There's been different kind of lab testing with decay rates of a styrofoam cup that came into existence in the last few years, and these dating methods dated the styrofoam cup at billions of years old. So these things are not false-safe methods. Obviously, a lot of these are used by evolutionists to prove the age of the Earth. So if the Bible says the age of the Earth is 6,000 years old, then we're misusing something, or something isn't being correctly represented. We can talk more about that in class, but essentially these are the half-lives as we know them. Some of them are spot on, some of them are not. Okay, but here's a sample problem. Okay, so let's look at this sample problem. It says phosphorus-32 has a half-life of 14.3 days. How many milligrams of phosphorus-32 remain after 57.2 days if you start with 4 milligrams of the isotope? Okay, so our starting mass is 4 milligrams. We don't have to convert it into grams or anything like that, because the problem is saying how many milligrams will remain, so we can keep that the way it is. Okay, we're also given the fact that phosphorus-32 has a half-life of about 14.3 days. So every 14.3 days, half the amount of the sample remains. So if I wait 57.2 days, I got to first compute how many half-lives that is, and that's pretty easy. You go 57.2 divided by 14.3 to figure out the number of half-lives that take, and then multiply the number of half-lives by the initial mass given, and you're good to go. All right, so looking at these things now, we can kind of, how do we solve this problem? The first step I want you to do is recognize that the number of half-lives now, it's not the answer to the question, but the number of half-lives equals, or is it going to be a function of the time elapsed in days times this new, essentially, conversion factor over here. This is a brand new conversion factor that we see here, okay? In this case, conversion factor for phosphorus-32 is 1 half-life every 14.3 days. So in this problem, the number of days elapsed is 47.2 days. So essentially what we did logically is what we're going to do mathematically. So number of half-lives equals, well, in this case, we've got 57.2 days elapsed times, and the half-life of phosphorus-32 is 14.3 days. So we essentially divide 57.2 by 14.3, and we come away with the number 4. So we have 4 total half-lives. Now, 4 total half-lives, we start now with 4 milligrams, and take half, 4 times half times a half times a half times a half is going to get us our resultant 0.25 milligrams. So that's how you do these problems. They're not too difficult. All right, you can continue working on these problems here. Whoops. Here, okay. So part of your homework tonight will be these 5 problems. You can tackle those 5 half-life problems. That'll be on sticker board for you. Okay, the rest of the chapter really dealt with a little fast on me. Just the decay series, okay. Decay series is a series of radioactive nuclides produced by successive radioactive decay until a stable nuclide is reached. The heaviest nuclide of each decay is known as the parent nuclide. The nuclides produced by the decay of the parent nuclide are called daughter nuclides. So in something called uranium-238 decay, you have an alpha particle released producing thorium-90, okay? So that's an example of this. A bigger picture of this is really a chain reaction, which is so here's an example of a neutron here hitting a uranium 235 massive nucleus, okay? And the series is called chain reaction. This is the series of decay that results, okay? So you have those two, more neutrons are produced, and you've got even more neutrons being produced here. And all of a sudden, you're going to have decay, okay? Obviously, the parent nuclide here would be the uranium-235. Through a series of chain, this is a chain reaction, you're going to see all these more stable nuclei produced. Okay, that's called chain reaction. The other thing I want you to be aware of in this chapter is a picture here of a nuclear power plant. Okay, as you can see in this model of a nuclear power plant, pressurized water is heated by fission of uranium-235. So you have fission going on. This water is circulated to a steam generator. The steam drives a turbine to produce electricity. Cool water from a lake or a river is then used to condense the steam into water. The warm water from the condenser may be cooled in the cooling towers before being reused or returned to the lake or river. So that is in a nutshell what's happening in a nuclear reactor. Just want you to be aware of how these things, the general idea behind these things. You won't be tested on this stuff, okay? And then you have fusion that happens in the sun, okay? Fusion is actually where two smaller nuclei are bound together to become heavier nuclei, whereas fission is a heavier nuclei decomposing the smaller nuclei. Okay, and here are some concepts at the end of the chapter here. All right, so that's the end of the chapter. You're going to be responsible for being able to work nuclear reaction equations of beta decay and alpha decay and the other electron capture and things like that. You're also going to have to work some half-life problems. So that's really what I'm going to be testing you on this chapter. So study up on that. I apologize for background noise. I'm doing this in my open-air office at CCS. But all right, so listen to this, do the problems that are listed on Sycamore. We'll see you in class.